Hi there, Nick. In a continuation from the previous video where we were calculating single cable resistances, we're going to look at R1 plus R2 cable calculations for radial circuits, and we're also going to look at ring final socket circuit testing as well. Okay. Like previously, we're going to be using table B1 and appendix B in the guidance note 3 and table I1 in appendix I in the on-site guide, utilising the milliohm per metre values for these cables at 20 degrees C. Okay, so that's the resistance of the cables per metre at 20 degrees C. So if you have a look at these tables in your on-site guide and your guidance note 3, you'll notice at the top, like the last video, conductor 1 column here on the screen for you is the line conductor, and conductor 2 column here like it is on the screen, but for you in the appendices that you're looking in, that conductor 2 is the protective conductor. So where we're utilising just one conductor, we utilise the conductor and the dash for where conductor 2 is, so we're disregarding conductor 2. But where we have a radial circuit, where we have one conductor and either a different size conductor or a similarly sized conductor, we can utilise the two columns that are applicable. So if you had two 1.5 millimeter squared conductors, you would use this value here rather than using that 1.5 and multiplying it by 2. It just stops you from doing that wee addition step. So for example, a 1.5 millimeter squared line conductor with a 1 millimeter squared protective conductor, 12.1 ohms, milliohms per meter, on the line conductor and 18.1 milliohms per meter on the protective conductor gives you an accumulated milliohm per meter value of 30.2. So this table means that you don't have to carry out those calcs. So let's try some basic calculations. We have here a 2.5 millimeter squared line conductor and a 1.5 millimeter squared protective conductor on our radial heating circuit that's 30 meters in length. Now remember, as we run through this, remember to pause the video, find the information and give the calculation a try as you go. Okay. So we're looking to calculate its expected R1 plus R2 value at ambient temperature. So we have a 2.5 millimeter squared line conductor, 7.41, 1.5 millimeter squared protective conductor, 12.1. The accumulated resistance of these is 19.51 milliohms per meter. Okay, from the table. So we take that 19.5 milliohms per meter and that length, and we look to calculate its R1 plus R2 value. Remember, the milliohm per meter value for the cable, when we multiply it by the length, we show there that it's directly proportional to the length. Okay, we're dividing it by 1,000 because we are starting in milliohms and we want to end up in ohms. Okay, so we take that 19.51, multiply it by that 30 meters, divide it by 1,000, and that gives us an expected R1 plus R2 value of 0.5853. Remember, your meter will show 0.59 because it only goes to 2 decimal places for the low resistance ohmmeter. Right. Second question, we have a 1 millimeter squared line conductor and a 1.5 millimeter squared line conductor and a 1 millimeter squared protective conductor on this lighting circuit, and the lighting circuit is 50 meters in length. So we have to calculate its expected R1 plus R2 value at ambient temperature. So again, back into these tables in Appendix I or Appendix B in the Guidance Note 3 or On-Site Guide and Guidance Note 3 respectively. So we have a 1.5 line 1 mil protective conductor, so 1.5 millimeter squared line conductor, 1 millimeter squared protective conductor, gives us an accumulated milliohm per meter value of 30.2 milliohms per meter. With that 50 meter length, if we throw that into our calculation, the milliohm per metre value times the length divided by 1000. That gives us 30.2 times 50 divided by 1000. Our expected R1 plus R2 value as a result of that calculation is 1.51 ohms. Okay, so you would confirm that your measured value and your calculated value are accurate. When we move slightly away from that for double value calculations, so R1 plus Rn or R1 plus R2 calculations, is when we're dealing with a ring final socket circuit. In a ring final socket circuit, because of the fact that it is while in a ring, we have to approach it slightly differently. So you'll see here we have a 2.5mm squared line and neutral cable with a 1.5mm squared protective conductor on this ring final socket circuit. The cable itself is the cables are 135 meters in length. So that means it leaves the board, runs round all the sockets and comes back to the board. And that overall loop length is 135 meters. So we have 3 stages we have to go through when we are carrying out these calculations. We have our stage 1 test where we carry out our little r1, our little rn, and our little R2 values. So that's the individual loop values for the cables. These are recorded on your test result sheet, okay, your schedule of test results. And then we have our stage 2 and stage 3 values. Our stage 2 values is our R1 plus Rn values, and our stage 3 values is our R1 plus R2 values. So we'll quickly run through these. So we have a 2.5mm squared line conductor. Rather than using the 2.5 and the 1.5 value, what we're going to do is we're going to use the 2.5mm squared conductor as an individual cable, and we'll use the 1.5mm squared conductor's milliohm per metre for the protective conductor. So we're going to use this 7.41 milliohms per metre value and this 12.1 milliohms per metre value. So we have a loop length of 135 metres. So utilising this 7.41, we have to calculate our R1, our little R1 and our little Rn loop values. Because these two cables are the same size, we just need to do one calculation. Okay, and when we measure our loops, we can confirm whether or not our calculation or our measured value is accurate in accordance to our calculation in the loop length. So we have our milliohm per metre value times the length. It's very much like the single cable calculations. So we take 7.41 times 135 divided by 1000. And that gives us an expected loop length resistance for little r1 and also an expected loop length resistance for little rn of 1 ohm. Okay. So that's we take our leads and we test end to end here at the board, round the ring, back to the other end, gives us a 1 ohm resistance. And then when we move on to our R1 plus Rn again, we connect onto our ends of the circuit at the board and test the loop length all the way around. Okay. Then we have to identify calculate our expected little r2 value. So we take that 12.1 milliohm per metre value and multiply it by the same 135 metres, again dividing it by 1000. That gives us an expected little r2 value of 1.63. Again, we go to our board, go to our disconnected ends of our ring final socket circuit, and we test end to end. So that's testing from one end all the way around back to the other, and we get a measured value of 1.63. We then take those values that we had measured and we pop them into our table here. This table is a great wee tool for you for doing ring continuity testing. Again, takes the thinking out of doing the calculation. Okay, if you can reproduce this before you start your calcs, all the heavy lifting has been carried out for you. All you have to do is plug the numbers in. So we take that 1 ohm for little r1 for our little our r1 plus rn calcs, and we plug it into the calculation. We take that r1 from the little rn and plug it into the calculation. Okay, so it's 1 plus 1 divided by 4. That gives us an expected R1 plus Rn value of 0.5 ohms. So 1 plus 1 is 2 divided by 4 gives us 0.5 ohms, but we have to take into account contact resistances through switches and connections at the front of the socket. So we're expecting 0.5 to 0.55 out of the front of the socket outlet. Okay, not from the back, but out of the front of the socket outlet. And then we repeat that process for our stage 3 to work at our stage 3 expected values. So we take our little r1 value, and this time we then take our little r2 value of 1.63, and that gives us 1.1 plus 1.63, so that gives us 2.63 at the top there, and then we divide it by 4. That gives us an expected r1 plus r2 value here of 0.66 plus the 0.05, so 0.66 to 0.71 of an ohm as an expected result out of the front of the socket outlet, taking into account contact resistance. So how do we get this divided by 4? Well, when we interconnect our ring final socket circuit at the board for stage 2, we connect our incoming neutral to our outgoing line, and we connect our incoming line to our outgoing neutral. Okay. If I was to grab these ends of the cables down here and open them up, I would get a figure of 8 on my loops. Okay, so you see the wee black links here. There's the representation of our black links here. On this line conductor here, you'll see I have a very short loop length back to this first link. There's my very short loop length back to this first link. This length here, between here and here, is 0.2 of an ohm. Okay, but the other side of that cable where that red probe's connected, we have 0.2 of an ohm, plus 0.2 of an ohm, plus 0.2 of an ohm, plus 0.2 of an ohm. That gives us 0.8 of an ohm on the other side. And that is mirrored on the other side where we have 0.2 of an ohm on the neutral going back to the link. There's a 0.2 of an ohm on the neutral, but that link there is connected to the long loop here on the line conductor, and then I have this long loop here on the neutral, 0.8 of an ohm, and that's connected to that short link there. So you'll see there we have 0.8 of an ohm and 0.2 of an ohm on one side of our parallel branches, and we have 0.2 of an ohm and 0.8 of an ohm on the other side. Okay, the accumulated resistance of this side is 1 ohm, the accumulated resistance of this side is 1 ohm. Basic parallel circuit, we've got two resistances the same size either side of a parallel branch. We take one of those resistances, so there's the accumulated 1 ohm, and we divide it by 2, and that gives us 0.5 of an ohm. Okay, or you could do a 1 over RT or a product sum calculation, whichever way you prefer. All right. As we move our leads around the ring, you'll see there this loop length here going back to the links increases. And you'll see that here as that representation there, where that's increased to 0.4 of an ohm. Okay, but as that loop length increases, this loop length here decreases. So this side here, the loop length decreases. You'll see there we have this accumulated 1 ohm, the sum of these two resistances either side is 1 ohm. If you know anything about parallel circuit calculations, again, we still have the same resistance either side, 1 ohm and 1 ohm. Our calculated value is 0.5 of an ohm. And as we run round the circuit, you will see there that the resistance values do not change either side. Okay, so we should get consistently the same value as we run round the ring. All right, okay. And you would repeat that for the little r1 plus little r2, not little r2, so the r1 plus r2 test that you would do between your line and your earth. Okay, and you're expecting to get the same